In 1947, Bell Laboratory scientists invented a new device they called the transistor. Communications technology suddenly, quietly, entered the new age of microelectronics. In any sophisticated manufacturing process, each step is the result of an interplay of skills, which advances the state of the art, day by day, hour by hour, at this very moment. This mask-making process at Western Electric is a first step in reducing an entire electronic circuit to a tiny modular chip. From this artwork, capable of infinite variation, more than 1,000 circuit patterns can be photographed onto an area the size of a 50-cent coin. In an environment as clean as an operating room begins the work of creating electronic miniatures. But we are operating in a new and different physical world, a world of minute quantities, minute currents, limited only by the speed of light. The goal is not the novelty of smallness. It is to make electronic pathways shorter and swifter. In one circuit, scores of transistors, resistors, capacitors, speeding, slowing, directing, switching the flow of electrons. The final product is a silicon chip, which to the naked eye may look no larger than a speck of dust. No larger than a speck of dust. Yet it's like exploring space, an inner space of shrunk proportions, a microcosmic world, where phenomena are generated by minute things. To enter it, we need radically different tools, like the laser. A focusing laser can search out imperfections in a master mask which might otherwise remain unseen, like these pinhole flaws. The clean rooms in which silicon wafers are manufactured demand extraordinary precautions. The least contamination can mean failure. Eventually, the process will move into an environment where people cannot go at all. In a process much like photo engraving, 1,000 integrated circuits will come to life on this single crystal wafer. How do you handle what may not be touched? These experimental wafers are guided by cushions of air. And how do you test what may not be touched and can scarcely be seen? Electronic probes have been developed that test each microcircuit. passing or ejecting, one by one. As new techniques shrink the size of the circuit, assembly line tools grow more complex. The hundreds of integrated circuits in this one wafer have to be separated into individual chips. A very precise kind of hair splitting. The kind of precision for which the laser seems ideally suited. Light can be used to measure diameters in units that are virtually infinitesimal. In fact, Western Electric pioneered the first scribing laser on the manufacturing line. Researchers are experimenting with cutting lasers with an eye to more extreme miniaturization. For techniques have already been developed, providing close to 1 million components per square inch of silicon. The delicate techniques employed in manufacture today suggest the incredible challenge to come. For even these microcircuits will seem enormous in the not too distant future. In the world of microelectronics, so far removed from human scale, there is still another dimension. Whatever the product or process, the component is destined to join a vast communications network. And for each component, no matter how tiny, there is a rule. It must be compatible with what exists and designed to work with changes still to come. What was learned in the laboratory is now routine on the production line. Finding a way to lead the minute currents from the microcircuit has been a continuing challenge. The tiny circuit must first be bonded to its fragile connections before it can take its place in an electronic network of billions of interacting parts. The expanding art of microelectronics was bound to have a profound effect on the communications industry. Without miniaturization, the picture phone would not be possible. It uses an array of the most advanced integrated circuitry and a camera tube whose minuscule target contains 840,000 light-sensitive diodes. We have learned to control size and number, and now it is possible to produce an instrument as complex as the picture phone in an economical form. Even as day-to-day production goes on, manufacturing engineers are developing original ideas for still newer products. Products that must be made at low cost yet of high quality, in great numbers, yet last indefinitely. And to make matters more complex, what is experimental today may be commonplace tomorrow. In research, the leading edge points surely toward tomorrow, when holography, the three-dimensional picture process that uses no camera, no lens, and only the laser's light, may offer a better way of making integrated circuit masks. Beyond the present, microelectronics brings us to still another threshold. An era in which the creative impulse and its acting out will be virtually simultaneous. Perhaps very soon, the convergence of technologies will allow a designing engineer working with a graphic computer to translate his conceptual idea directly to a three-dimensional prototype. The elements already exist. They exist because of the endless effort to extend the human ability to communicate, to extend man's brain, his eyes, his hands. The elements exist because of man's entry into the microelectronic world.